everyone, welcome to part 2 of chapter 10. Last time we got an introduction to chemical equations. We learned how to write chemical reactions and how to balance them so that they obey the law of conservation of matter. We also learned how to take a chemical reaction written out in words and convert that into a chemical equation used to describe that reaction. So today we are going to learn all about the different types of reactions. There are 5 different reactions that we will cover today, and by the end of today's lecture, you'll know how to identify them and be able to predict the products and balance those chemical reactions. So, lots to do today. Let's get going. So, why do chemical reactions occur in the first place, right? Sometimes we mix things together and a reaction doesn't happen. For example, if we put some salt in water and we mix that together, the salt dissolves, but it doesn't magically turn into iced tea, right? It's just a mixture of salt water. So how come when we add things together, sometimes they react and sometimes they just mix? And mixing is a physical process, right? So not a chemical reaction. Well, we have these driving forces that can tell us that a chemical reaction will occur. So these are things that will be produced during a reaction that kind of make the reaction go, if you want to think about it that way. So the first one is formation of a solid. Remember, when we were studying the characteristics of a chemical change, one of those was a formation of a precipitate, right? When we poured together 2 clear liquids and they made a solid. That's what we're talking about here. So forming a solid is a driving force that causes a chemical reaction to happen. Another one is formation of a gas. Remember, that was also one of our characteristics of a chemical change. We would observe bubbles, right, if there was a gas forming. And then the last one would be the formation of water. This is typically in an acid-base reaction, which we'll study in a couple chapters. So if we form water, that's also a driving force. So forming a solid, a gas, or water will cause a reaction to happen. If any of those observations occur, right, formation of a solid, we see bubbles, we produce pure water, then we're likely having a chemical reaction. Not definitely, but likely. And we'll learn more about predicting the outcome of mixing these reactions as we go through this chapter. So here are 5 types of chemical equations. So we have combination reactions and decomposition reactions. Those are essentially opposites. And then we have combustion reactions, which are kind of a special type of reaction. We'll look at that. And then single displacement and double displacement reactions. So these are the 5 types of reactions that I want you to be able to know and be able to recognize in this chapter. We are going to spend pretty much all of today's lecture focusing on that. So in a combination reaction, it's exactly what it sounds like. 2 or more elements are going to combine to make one product. So like this, we have one thing, so we have 2 individual things and they combine together to make one thing, okay? So a combination reaction is just stuff combining together. So this A and the B, they can both be elements, they can both be compounds, they can be an element in a compound, whatever it is, as long as they end up kind of smooshed together into one single product, then we call that a combination reaction. So here's some examples. So in the first one, we have 2 elements. Remember that sodium is by itself because it's not a diatomic molecule. But chlorine is a diatomic molecule because it shows up in Hofbrinkel. That's why it has this 2. But we recognize this as a combination reaction because we have 2 elements reacting to form a compound. In the next example, we have 2 compounds, and they react together to form a new compound. But again, it's 2 individual pieces that are making just one piece. So that's how we're going to recognize a combination reaction. 2 individual pieces make one piece. Okay? Here's an example of a combination reaction that I think is super interesting. Okay, so we have potassium, which is kind of like a soft silvery metal, and we have chlorine, which is a toxic green gas. It's super poisonous. It's essentially like if you think about Disney movies and the villain always has like a green gas, I always kind of think that to me looks like chlorine gas because I'm a chemist, but it's a toxic, poisonous green gas. But when we react a silvery metal of potassium with this toxic green gas, which is chlorine, we get potassium chloride, KCl. So this is a combination reaction. Alrighty, so this is a really typical example problem. This says predict the products of the reactions and balance the resulting chemical equations. So here's our first one. This is sodium and chlorine. We've actually already seen this problem, but I wanted to give you one that you were familiar with so we could kind of understand the process we would go through to predict the products. So here we have two single elements, and the first thing we really need to do is determine what type of reaction these will undergo. Since they're both just single elements, the only type of reaction they can do is a combination reaction. We'll learn about other reactions a bit later, but that's the only one we've learned so far anyways, so that should clue you in. So when we see this, sodium and chlorine, they are going to combine together to make one product. But when they combine together, they are going to make an ionic compound because sodium is a metal and chlorine is a nonmetal. Anytime you see a metal and a nonmetal making an ionic compound, I want you to think ionic compounds are made of ions. Therefore, I need to write out the ions and circle and switch. So sodium is Na+, and chlorine is Cl-. And a lot of times people right here will be like, whoa, wait, hang on, what happened to this 2? Remember, that 2 is only there because chlorine is a diatomic molecule. Chlorine shows up in Hofbrinkel. That's why that 2's there. Anytime chlorine is sitting by itself, it needs to have a 2 after it, which is why sodium doesn't have a 2 because it doesn't show up in Hofbrinkel. So that 2 is only there when chlorine is sitting by itself. Now chlorine is going to be put together in an ionic compound, so we don't need that 2 anymore. Okay, so when you are making these ionic compounds, do not take those subscripts with you, just figure out the element and its ion. So here we have Na+ and Cl-. So that 1+ and the 1- exactly cancel out and we get NaCl. So the next thing we need to do though is balance our equations. From here on out, anytime you write a chemical equation, whether I tell you to or not, you definitely need to balance it. I may not remind you, but just remember, balanced equations allow us to obey the law of conservation of matter. So anytime you see a chemical reaction, your first thought should be, oh, I gotta balance this. So let's balance it. We have 2 chlorines on the left-hand side, and we need to have 2 chlorines on the right, so we'll put a 2 there. That now gives us 2 sodiums on the right, and we need to have 2 sodiums on the left as well, so we'll put a 2 here. And now that equation is balanced. Let's try another. So this one has magnesium and fluorine. Again, we have 2 elements, so the only reaction they can do is a combination reaction. So they're also going to make an ionic compound because magnesium's a metal and fluorine's a nonmetal. So we get their ions. Mg makes a 2+ and fluorine makes a 1-. Those charges are not equal and opposite. So we need to circle and switch. So that 2 is going to go to the fluorine. So that makes MgF2. Okay, and if you look, this equation is already balanced. So we don't need any coefficients. All right, let's try this one. This is aluminum reacting with fluorine. So again, these are just 2 individual elements. So that's how we know they have to undergo a combination reaction. So when aluminum reacts with fluorine, they are also going to make an ionic compound because aluminum's a metal and fluorine is a nonmetal. So again, ionic compound, we have to write out our ions. Aluminum makes a 3+ and fluorine makes a 1-. So these charges are not equal and opposite, so that 3 has to go to the fluorine and we get AlF3. Okay, so looking at this, you'll notice that our fluorines are not balanced. Anytime you have a 2 and a 3, remember that those are going to balance to 6. So we're going to make this one multiplied by 2 and this one multiplied by 3 so that we will have 6 fluorines on each side. Then we need to balance our aluminums. We have 2 aluminums on the right, So we need to put a 2 here so that we also have 2 aluminums on the left. All right, let's go ahead and go on to our next type of reaction. Our next type is a decomposition reaction. This is essentially the opposite of combination reactions. We are going to have one thing, one compound, and it's going to split into 2 or more products. So it can split into 2 elements, it can split into 2 compounds, it can split into an element in a compound, it could split into 3 things, right? But the whole way that we're going to recognize this is we're just starting with one reactant. And usually what happens is we heat this one reactant and it decomposes. It falls apart along the way. But again, the key here is you're just going to start with a 1 at the beginning. So here's some examples. So this one, we are heating lead-4 oxide and we're making lead-2 oxide and oxygen gas. Or if we heat calcium carbonate, we can get calcium oxide and carbon dioxide. Or if we decompose hydrogen peroxide, we can get water and oxygen gas. So all of these are decomposition reactions because we're just starting with one reactant and we're making multiple products. Okay, that's how we will recognize a decomposition reaction. This is the only type of reaction that I will not ask you to predict the products. Some of these products can be really tricky to predict, and so you are not responsible for predicting products of decomposition reactions. All of the other types of reactions are fair game, and I will ask you to predict those products, just not for decomposition. So this is an example of a decomposition reaction. We have mercury 2 oxide, and we heat it. Remember, this triangle over the arrow means heat. And when we heat it, it decomposes into mercury liquid and oxygen gas. So we can actually recognize one of the driving forces of this reaction is the production of oxygen gas. So again, I won't ask you to predict the products of these decomposition reactions. I may ask you to identify them, right? Tell me this is a decomposition reaction, and you may have to balance it, but you won't have to predict the products. All right, our next type of reaction is a combustion reaction. Combustion reactions are really straightforward to memorize or to recognize because in a combustion reaction, we always have a hydrocarbon reacting with oxygen gas. And by hydrocarbon, I mean something that's got carbon and hydrogen and maybe oxygen too. Typically, this is just things are being burned, like your burner in your, house, right? If you were cooking on your stove, that's a combustion reaction. Or if you have a bonfire in your backyard, that's a combustion reaction too. So here's our general equation. So we have some hydrocarbon reacting with oxygen gas to produce carbon dioxide and water. These reactions are really easy to predict the products because the products are always carbon dioxide and water. It doesn't matter what your hydrocarbon is, it's always going to make the same products, carbon dioxide and water. So if I ask you to predict the products of a combustion reaction, you should be like, oh, easy one, carbon dioxide and water. Okay? The only thing that's ever going to change is this here. It's always going to react with oxygen gas. It's always going to produce carbon dioxide and water. So here's an example. So this is pentane. Pentane is reacting with oxygen gas to make carbon dioxide and water. So again, the only thing that's ever going to change is this hydrocarbon. It's always going to react with oxygen gas. It's always going to produce carbon dioxide and water. You will just be responsible for balancing that equation. I will remind you, and we talked about this in the last lecture, that combustion reactions are the trickiest to balance. If you look here, you've got some larger numbers than you see in other types of equations. This is often true for combustion reactions. Okay, just remember to always balance the carbons first, then the hydrogens, and then the oxygens. And you'll usually be good to go. So let's try this one. This says predict the products and balance the following combustion reaction. Again, this should be an easy one. If we're predicting the products, you can say, oh, I see that a hydrocarbon is reacting with oxygen gas. Anytime a hydrogen is reacting with oxygen gas, that is a combustion reaction. Therefore, the products are always carbon dioxide and water. So easy one, predicting the products wise. So our next step now is to balance it. And remember, combustion reactions are tricky to balance. Okay, so let's go ahead and kind of keep our tally down here. We have carbon, hydrogen, and oxygen on each side. So right now I have 10 carbons on the left, 22 hydrogens, and 2 oxygens. And on the right, I have 1 carbon, 2 hydrogens, and 3 oxygens. So we definitely have some balancing to do. The first thing I'm going to do is to multiply my carbon dioxide by 10. That will give us 10 carbons, but now it gives us 20 oxygens there, plus another one from water. So I'm getting a total of 21 oxygens. That's a lot. All right, now let's go ahead and balance our hydrogens. So we have 22 hydrogens on the left and only 2 on the right. So I'm going to multiply this by 11. When I do that, that gets me 22 hydrogens. But it also changes our number of oxygens. So we have 20 oxygens over here, 2 times 10, plus another 11 oxygens from water gives us a total of 31 oxygens right now. So usually people get to here and they're like, wait, I need to put something here to multiply by 2 that's going to get me 31. But I can't multiply something by 2 and get an odd number, so something went wrong. Not quite. It's just one of those, like I said, sometimes combustion reactions, this happens. And when you do that, just go through and double all of the coefficients that you already have. So instead of this being a 1 in front of our C10H22, now I'm going to put a 2. Instead of this being 10 carbon dioxides, now I'm going to make it 20. And instead of there being 11 waters, now I'm going to make 22. So all I've done is go through and double everything I worked on before. Okay, so now if we think about the number of oxygens on that right-hand side, because oxygen's what we're trying to balance, now I have 40 oxygens from carbon dioxide and 22 oxygens from water, which is giving me 62 oxygens total on the right-hand side, which means this number here is 31. 31 times 2 will get us 62. So I know that's a lot of work for these combustion reactions, but hopefully you see the process that I'm going through. Just always make sure to balance them in the order of carbon, hydrogen, and oxygen. All right, now let's learn about a new type of reaction. So single displacement reactions are kind of specific. An uncombined element is going to replace an element in a compound. So it doesn't make a lot of sense by words. Let's look at what that means. So here we have, this is a compound and this is an element. The way that you will recognize single displacement reactions is it's always going to be an element reacting with a compound every single time. Okay, so if you have some other combination of things, then it's not a single displacement reaction. A single displacement reaction must be an element plus a compound, or here you see it backwards, compound plus an element. Doesn't matter, but it's always got to be those two things. Okay, so what's going to happen is here we have our single element, which is zinc. Zinc is a metal. So that means this metal is actually going to go and displace the other metal, okay, which is copper. So in this, the zinc displaces the copper, so now the zinc is where the copper was and the copper is where the zinc was. So the reason that the zinc displaced the copper is because zinc is a metal and so is copper, so the metal kicks out the metal, okay? If this compound had been reacting with a non-metal, we would have swapped out the non-metals. But this is how you'll recognize a single displacement reaction. An element and a compound, and that element kicks out one of the elements in the compound. Here's some more examples. So this one we have zinc and hydrochloric acid. This is a cool reaction. I like to do it in class because it produces hydrogen gas, and hydrogen gas is flammable. And so you can actually light the hydrogen gas that's being produced in this reaction. It'll make a nice little pop. But here the driving force for this reaction would be the production of a gas. But let's look and see how we recognize this as a single displacement reaction. Do you see here, this is an element and a compound. So again, every time you see an element and a compound, that's going to tell you this is a single displacement reaction. So here, zinc is a metal, so it would normally go and swap out the metal. But you can see that hydrogen and chlorine are both non-metals, so a lot of people are like, well, what now? Zinc is going to switch out then with the cation. sometimes hydrogen acts like a metal. So zinc will switch out with hydrogen. So now the zinc ends up bonded to the chlorine and the hydrogen ends up by itself. So here's some more examples. So we have, again, an element and a compound. So this element, iron, is a metal, so it's going to kick out the copper. So then the copper will end up by itself and the iron will end up bonded to that sulfate. In this example, again, we have an element and a compound. Chlorine here is a nonmetal, so it's going to go kick out the nonmetal, which is iodine. So then iodine ends up by itself and potassium ends up bonded to chlorine. So it depends on whether your single element that's reacting is a metal or a nonmetal. If it's a metal, it'll kick the metal out of the compound. If it's a nonmetal, it'll kick the nonmetal out of the compound. So let's try this one. This says predict the products of the reactions and balance the resulting chemical equations. Okay, so this is aluminum plus hydrochloric acid. So aluminum is a metal, but again, we don't have any metals in hydrochloric acid. But like I told you, sometimes hydrogen acts like a metal. So in this case, that aluminum is going to kick out the hydrogen. So that means hydrogen is going to end up by itself. But remember, hydrogen is a member of Hofbrinkel. So anytime hydrogen is sitting by itself, it must have a 2 after it. Okay? So now we have hydrogen sitting by itself and aluminum is going to be bonded to the chlorine. When aluminum bonds to the chlorine, that's a metal bonding to a nonmetal. That will make an ionic compound. Therefore, we need to write out our ions and circle and switch. So aluminum is Al3+, and chlorine is 1-. So when we circle and switch, that 3 is going to go to the chlorine, and that will make AlCl3. Okay, now we need to balance this. Okay, it doesn't really matter where you start. This one is a little bit tricky in that, do you see that both the hydrogen and the chlorine, like we have 2 hydrogens on the right-hand side and 3 chlorines on the right-hand side? That's going to mean that this is actually going to have to be 6 hydrochloric acids to balance both the hydrogens and the chlorine. It's a little bit tricky. I'll let you play around with it on your own, but that's how that's going to play out. And then once we balance those hydrogens and chlorines, we'll have 2 aluminums on the right-hand side, which means we will need to put a 2 here on the left-hand side. Okay. Now, let's try this one. So this is magnesium plus aluminum nitrate. So again, we'll recognize this as a single displacement reaction because this is an element reacting with a compound. This element is a metal and therefore it's going to switch out with the other metal. So that means aluminum will end up by itself. You'll notice that aluminum is not a member of Hofbrinkel, so it does not need a 2 after it. All right, now let's figure out the formula of our new compound. So magnesium is a metal and nitrate is a polyatomic ion. That means we will be making an ionic compound. Therefore, we need to write out our ions and circle and switch. So magnesium is Mg2+, and nitrate is NO3, 1-. These charges are not equal and opposite, so we need to circle and switch. So this 2 is going to go to the nitrate. Remember, when we need 2 of a polyatomic, we are going to put that entire polyatomic in parentheses and put the 2 on the outside. Now we need to balance it. Do you see that we have 3 nitrates on the left and 2 nitrates on the right? That means this is going to need to balance to 6. So I'm going to put a 2 here and a 3 here to balance out my nitrates. Then I can put a 3 on the left here to balance my magnesiums and a 2 on the right to balance my aluminums. All right, one more example. This is sodium chloride plus fluorine gives, and we need to figure that out. Again, we'll recognize this as a single displacement reaction because we have a compound and an element. This element is a nonmetal, right? Fluorine is a nonmetal, so it will switch out with the nonmetal. So when that happens, chlorine now will end up by itself. Okay, when chlorine ends up by itself, it needs a 2 after it because chlorine is a diatomic molecule and is a member of Hofbrinkel. So we get that 2 there. Now we need to make our formula for sodium and fluorine. Sodium is Na+, and fluorine is F-. These are equal and opposite, so we do not need to circle and switch. We'll just put them together. Then we need to go through and balance all of our different chemicals. So we've got fluorine. There are 2 fluorines on the left and only 1 on the right, so I'll put a 2 there. And then a 2 here will balance both our sodiums and our chlorines. Alrighty, let's go ahead and do some practice problems. For each of these reactions, figure out whether it's a combustion reaction, a decomposition reaction, a combustion reaction, or a single displacement reaction. So for this problem, you just need to identify the type of reaction. You don't need to predict products or balance or anything. Just see if you can identify the type. So go ahead, pause here, and come back when you're ready to see the answers. Alright, let's go through this. So this first one, we have an element and an element reacting to form a compound. So this first one is a combination reaction. The only thing 2 elements can do is combine together. Let's look at the next one. So again, we have an element, and they're reacting to make a compound. So again, the only reaction that 2 elements can do is combination reaction. For our next reaction, do you see it's just 1 reactant? Anytime you just have 1 reactant, the only thing that reactant can do is decompose, which is what it does. It makes 2 different products. So this is a decomposition reaction. In our next reaction, you can see that we have an element reacting with a compound. Remember, when we have an element reacting with a compound, that is going to be a single displacement reaction. Our next one is one that I told you, you should try and be able to recognize. Here we have a hydrocarbon. It's reacting with oxygen gas to produce carbon dioxide and water. Anytime you have that specific scenario, a hydrocarbon reacting with oxygen gas to produce carbon dioxide and water, that is going to be a combustion reaction. So our next one, we have calcium carbonate is reacting, right? Is decomposing, essentially. We have, again, just 1 reactant. Therefore, the only reaction that can happen is decomposition. The only thing it can do is break down. And then in our last one, that is also a single displacement reaction because we have an element reacting with a compound. And you can see that magnesium kicks that zinc out, so zinc ends up by itself, and magnesium ends up bonded to the chloride. Remember, it doesn't matter the order that you write, like I could have written, zinc plus magnesium chloride. These are the same thing. It doesn't matter the order that you write them in, as long as they end up on the correct side of the arrow. All right, our last type of reaction that we are going to talk about today is double displacement reactions. So when we have a double displacement reaction, 2 elements in the reactants are going to trade places, okay? So this is different from when we saw single displacement reactions, because remember, in a single displacement reaction, we had an element reacting with a compound. Here, in a double displacement, this will always be a compound reacting with a compound, okay? When we have a compound reacting with a compound, essentially, 2 things are going to switch places. So here, we had the oxygen and the sulfur switching places. So now the magnesium is bonded to the sulfur and the calcium is bonded to the oxygen. So you have 2 elements that are going to switch places. So here's our example. So this has A and B plus C and D. So in this example, B and D have switched places. Okay, so A is bonded to D and C is bonded to B. Again, a double displacement reaction will always be 2 compounds. So when we're trying to kind of predict the products, I want you to think about it like when you learned how to FOIL in algebra. The first and last ions go together and the inside ions go together. So we would see this one. This first one is silver nitrate plus sodium chloride. We will recognize this as a double displacement reaction because it's 2 compounds. When we have 2 compounds, you'll see double displacement and 2 of our elements are going to switch places. So here, the silver will bond to the chlorine to give us silver chloride. So again, the first and last will bond together, and then we'll get the two middle bonded together, so sodium and nitrate, and that will make sodium nitrate. So another example, right, again, the second one is also a double displacement reaction because we have two compounds. Okay, so when we have two compounds, it's double displacement, and two of our elements are going to swap places. So our first and our last elements will go together, our first and our last, polyatomics. So we get potassium nitrate, and then our middle ones will go together, so barium and sulfate. So again, if you just always follow that same kind of pattern, I think it makes it easy to predict the products. So a lot of times when we're looking for this driving force, it's really easy to see in these double displacement reactions. And all of our next lecture is actually going to focus on double displacement reactions. They're really common in chemistry because we typically react things as compounds. So in a double displacement reaction, when we have two compounds reacting, that's really common in chemistry. So our evidence of a double displacement reaction are going to be mostly those characteristics of a chemical change that we've talked about before, like heat production, right? Usually these reactions are exothermic, and so you'll feel like the Erlenmeyer flask getting warmer when this reaction happens. We will also sometimes see the formation of a precipitate, and again, that's going to be a big focus of the next lecture. You may also see gas production, so bubbles. But again, a lot of times with these double displacement reactions, we will actually visibly see the reaction taking place. So this example here is lead nitrate and potassium iodide, and it makes this cool lead iodide solid. That's what the yellow is that we're seeing here. Very, very cool. Alrighty, go ahead and pause here and complete problems number 3 through 6 on the Chapter 10 lecture worksheet. Once you're done, come back and we'll keep going. All right, let's talk more about double displacement reactions. Double displacement reactions will actually be the focus of all of the rest of today's lecture. So remember, in double displacement reactions, the ions of two compounds, right, two of our elements are going to change places, and they do this in an aqueous solution. Okay, so anytime we're talking about double displacement reactions, we're talking about two different aqueous solutions that have been combined together, and when they do that, they form new compounds. So here we have AX and BY, and X and Y are going to be kind of trading places. So now A is going to be combined with Y, and B is going to be combined with X. One of the compounds that we're forming is typically a precipitate. Like most of the time, that's what's happening, is that one of these two will form a precipitate. And remember, a precipitate is an insoluble solid. Sometimes one of these is an insoluble gas that bubbles out of solution. Normally this will be something like hydrogen or sometimes carbon dioxide. Or it can be a molecular compound that's formed. And in this class, usually for forming a molecular compound, it's going to be water. So here are our types of double displacement reactions. So like I said, the first type is the most common. That will be the formation of a precipitate. This is going to predict solubilities based on our solubility table. And I will be giving you a solubility table. So our insoluble products are going to be indicated by an S. So like this is our insoluble product. That would be our precipitate that's being formed. You'll notice that the two solutions that we're adding in the beginning are both aqueous. That's typically how this is going to play out. We're going to pour together two different aqueous solutions, and they are going to form an insoluble solid. Typically, the other thing will be aqueous. Not always, but most of the time. Another type of reaction that we can do is an acid-base neutralization reaction. So here we'll recognize that this compound is an acid because it starts with an H in the front, and this is a base because it ends with an OH. Anytime you have an acid plus a base, it's always going to make a salt and water. So water formation is what's driving this reaction. when you hear this term salt in chemistry, it doesn't mean table salt. I mean, in this example, it did, but it doesn't always. So a salt that's being formed, this is just an ionic compound. Okay, so when we have an acid plus a base, that's going to make an ionic compound and water. Like this example, we made sodium chloride and water. And then our last type of double displacement reaction is probably our least common in this class, and that would be gas formation. So here, hydrochloric gas is being formed. Okay, we're going to look at a couple of these types of reactions, but we are going to focus mostly on formation of a precipitate and acid-base neutralization. All right, so I have a few solubility rules for you to memorize because, it's been a minute since we memorized something in this class. Okay, I don't have very many rules for you to memorize. Most of the time, I will give you a solubility table. These solubility rules I want you to memorize are ones that are always soluble. So ionic compounds that contain an alkali metal cation or the ammonium ion are always soluble. So remember, alkali metals are in group 1A. So all of these elements are in group 1A. Lithium, sodium, potassium, rubidium, cesium, and francium. Well, francium doesn't really make compounds, so we just have these. But these, anytime you see them in a compound, that means that compound is always aqueous. It's always soluble. So like sodium chloride is soluble, or lithium chloride is soluble, or potassium chloride is soluble, right? Because they have an alkali metal. This is also true for the ammonium ion. Remember, that's our one polyatomic cation. So if you see ammonium, that's also going to be soluble. And just as a reminder, if it's soluble, that means that it dissolves in water. So if we have a nitrate ion or an acetate ion, that means they are also soluble. These are going to be our soluble anions that I want you to remember. Okay, so again, not a ton, just if you see these certain elements or polyatomic ions, I want you to recognize that that compound is always going to be aqueous. It's always going to be soluble. The reason I have you memorize these is mostly so that these problems will go faster. If you can notice, like, oh, that has sodium in it, therefore it's aqueous, or oh, that has nitrate in it, therefore it's aqueous, these reactions will be a lot faster for you to do. So it's a bit out of convenience, but it's also really handy to know. So if something is not one of those that you're supposed to memorize, I will provide for you this solubility table. And let's take, for example, if we were trying to figure out whether sodium chloride is soluble in water. We know that sodium chloride is soluble because it has sodium, which is an alkali metal, therefore it's always soluble. But let's say we didn't know that. The way we would use that is we would see, okay, here's sodium and here's chloride. Here's the intersection. That tells us that sodium chloride is aqueous. Let's try another one. Let's say instead we had silver chloride. Okay, if we wanted to find out whether silver chloride was aqueous, we would use silver and chloride again, and we would find their intersection. Do you see that this has an I? That I tells you that this is insoluble. And so when we were writing silver chloride, that would be forming our precipitate, so we would write S. Okay, so when you find this intersection, it's either going to tell you that it's aqueous, which means it's soluble, or it's going to have an I, which tells you it's insoluble. Okay, let's try this out. This says classify each of the following compounds as soluble or insoluble in water. So I want you to go ahead and pause here and see if you can use those solubility rules that I was going to have you memorize or the solubility table to determine whether these are soluble or insoluble in water, because that's going to be a really crucial skill moving forward. So go ahead, pause here, try this out, and then come back when you're ready to see the answer. Alrighty, so for our first one, we see silver nitrate. So if we were, thinking about our solubility rules we have to memorize, we see this has nitrate in it. Nitrate is always soluble. Therefore, this entire molecule is soluble, and this would be aqueous. Okay, let's look at the next one. So this doesn't follow any of our rules. It doesn't have an alkali metal, right? It doesn't have ammonium. It doesn't have nitrate. It doesn't have acetate. So we don't automatically know whether it's aqueous or not. So we would go back and use our table. So we're doing calcium sulfate. So here's calcium, and then sulfate is over here. So to find their intersection is right here. So there's an I. That I is telling us that it's insoluble. Therefore, calcium sulfate would get an S. That tells you it's going to be a solid. Okay, so insoluble. So as long as it's not one of those that you have to memorize, you can use that solubility table to figure out, okay, is it soluble or not? Let's look at the next one, potassium carbonate. Okay, we see potassium there. Potassium is an alkali metal. That's one of those that we needed to memorize. So anytime we see potassium, that means it's always going to be aqueous. It's always soluble. All right, let's try and predict the products of some double displacement reactions. We predicted the products of a lot of other types of reactions already, but we haven't done double displacement yet, so let's go ahead and give that a go. So this says write the equation of the reaction between aqueous solutions of hydroiodic acid and sodium hydroxide. Do you see that I haven't given you the formulas of our compounds? I've given you words, just like we did in the last lecture. Okay, so the first thing we'll need to do is figure out our formulas of hydroiodic acid and sodium hydroxide. So when we see hydroiodic acid, anytime we see a hydroic acid, that's a binary acid. That means that hydrogen is just bonded to iodine. So this will be HI. Okay. When you see sodium hydroxide, that's an ionic compound, right? A metal and a polyatomic. Sodium is Na plus and hydroxide is OH minus. Those charges are equal and opposite, so we just get NaOH. So we're having hydroiodic acid and sodium hydroxide. The H in the front tells us that that's an acid, or, the name said acid. And the OH in the back, that's telling us that this is a base. Anytime we have an acid plus a base, it is always going to give us a salt and water, okay? Every single time. So we just need to figure out what the formula of this ionic compound will be. So an acid plus a base gives us a salt and water. So the part of these compounds that's forming the water is the H from the acid and the OH from the base. H plus OH will give us H2O. So that's what's forming our water. The salt is going to be formed from anything that's left. So we have iodine and sodium. So sodium is Na plus and iodine is I minus. These charges are equal and opposite, so we're just getting NaI. So our acid plus our base will give us a salt and water. So then we need to go through and figure out the phases of matter for all of these things. Anytime you see an acid, that's always going to be aqueous. And anytime we see a base, that's also going to be aqueous most of the time. But I would go through and check. This one is aqueous because it's attached to sodium. And everything attached to sodium is always aqueous. For that same reason, sodium iodide is aqueous because it has sodium, okay? And then our last one is water. Anytime you see water, water is always going to get a cursive L, okay? Water is going to be a pure liquid. All other, quote unquote liquids, we give the term aqueous because there's stuff dissolved in water. But anytime you write water, you're going to write a cursive L to indicate that that is a pure liquid. Let's try another one. This says to write the balanced equation for the reaction between aqueous solutions of barium chloride and magnesium sulfate. Okay, so the first thing we need to do is figure out what barium chloride and magnesium sulfate are. So These are both ionic compounds, so therefore we need to write out the ions and circle and switch. So barium is Ba2+, and chloride is Cl-. These charges are not equal and opposite, which means we need to circle and switch. So that 2 is going to go to the chlorine and make this BaCl2. Magnesium sulfate is also an ionic compound, so let's write out the ions. Magnesium is 2+, sulfate is 2-. These charges are equal and opposite, therefore we get MgSO4. All right, so that's our reaction that's happening. We're reacting barium chloride and magnesium sulfate. Since these are both compounds, this is going to be a double displacement reaction. Okay, so like I said before, I would think of foiling this. So barium is going to react with the sulfate and magnesium is going to react with the chloride. So the first and the last, and then the inner ones. When barium reacts with sulfate, we have Ba2+ and SO4 2-. Those charges are equal and opposite, therefore we're going to get BaSO4. When magnesium reacts with chlorine, we're getting magnesium reacting with chlorine, okay, Cl-. You'll notice that 2 from BaCl2 does not show up when I'm going to circle and switch. The reason for that is that 2 got there because we circled and switched because barium was a 2+. When we recircle and switch, we have to figure out what that subscript would be so we don't take it with us. So we just have magnesium and chlorine. These charges are not equal and opposite, so we have to circle and switch, and we'll get MgCl2. So we'll get barium chloride plus magnesium sulfate is going to give us barium sulfate and magnesium chloride. Then we need to go through and figure out the states of matter. So we would use the solubility table for this. You can see in the problem, it tells us our starting materials are aqueous solutions. So we already know both of these are aqueous because it says it in the problem. For our products though, we need to go and look at our solubility table. If you were to check it out, barium sulfate will have an I, and that tells us it's going to be insoluble. Therefore, we put an S to indicate that it's going to make a solid. Magnesium chloride, on the other hand, will have an AQ. That means it is aqueous and will dissolve. All right, let's try another one. This one says balance the equation for the reaction between aqueous solutions of potassium carbonate and barium chloride. So again, our very first thing that we need to do is figure out the formulas of our starting material. So potassium carbonate is K+ and CO3 2-. So that's potassium and carbonate. Again, these charges are not equal and opposite, so we're going to need to circle and switch. That 2 is going to go to the potassium, and we'll get K2CO3. Then we have barium chloride. So barium is Ba2+, chlorine is Cl-. These charges are not equal and opposite, so we need to circle and switch. So that 2 is going to go to the barium, and we get BaCl2. Okay, so that's our starting material. So again, the way that we know this is a double displacement reaction is we have 2 different compounds reacting together. So when we have 2 different compounds, we get double displacement, and we need to figure out our new products. So potassium will end up with chlorine, and barium will end up with carbonate. Okay, so when potassium reacts with chlorine, we're getting K+ and Cl-. Those charges are equal and opposite, so we'll just get KCl. When barium, Ba2+, reacts with carbonate, which is CO3 2-, those charges are also equal and opposite, so they will cancel out, and we'll get BaCO3. So we'll get potassium carbonate and barium chloride react together to make potassium chloride and barium carbonate. And then obviously you would need to go through and balance our chemical equation. Our problem told us that our starting material were aqueous solutions. So we already knew that these were aqueous. But for the other 2, right, we'll see potassium here. Anything with potassium is always going to be aqueous. So we didn't need to look that one up. But barium carbonate doesn't follow any of our automatically soluble rules. So we need to look up barium carbonate on our table. If you find the intersection of barium and carbonate, you'll see that there is an I there. That's telling you it's insoluble and therefore makes a solid. All right, I want you to go ahead and try this problem out. Okay, this is a predicting products practice problem, and a lot of people find these to be kind of tricky, so I do want you to really give this a go. When you're thinking about these, first figure out what type of reaction it will undergo. That will help you to predict the products. Like, is it a combination reaction? Is it a double displacement? It is a combustion, right? Figure out the type of reaction that will happen first, and then predict the products, and then balance it. All right, go ahead and pause here and give this a go, and then come back when you're ready to see the answer. Alrighty, so for our first one, we have two different compounds. When we have two compounds, that will be a double displacement reaction. Okay, so barium chloride and sulfuric acid. So what we'll do is we'll put the two outside ones together and the two inside ones together. So when barium reacts with sulfate, we get Ba2+ and SO4 2-. Those charges are equal and opposite, so they cancel out, and we will get BaSO4. And then hydrogen will react with chlorine. Hydrogen is H+, and chlorine is Cl-. So we're just getting HCl. Then we need to go through and balance this reaction. Do you see that there's two hydrogens and two chlorines on the left-hand side, but only one of each on the right? That means we're going to get a 2 here. And now it's balanced. And again, this was a double displacement reaction because, again, there were two compounds that were reacting. All right, let's try the next one. So the next one has a hydrocarbon reacting with oxygen gas. Hopefully you recognize this as a combustion reaction. The products of all combustion reactions are carbon dioxide and water. Okay. So now what we need to do is balance this combustion reaction. Remember, I like to do carbon, hydrogen, oxygen for combustion. So first we'll balance our carbons. So there's 6 on the left, so we'll put a 6 here. And then we'll balance our hydrogens. There's 12 on the left, so that means we need a 6 there. So now we need to balance our oxygens. We have 12 oxygens coming from carbon dioxide, 2 times 6, plus another 6 oxygens coming from water, which gives us a total of 18. Therefore, this will be a 9. All right, let's try the next one. The next one is an element reacting with a compound. Anytime you see an element reacting with a compound, that's going to be a single displacement reaction. And that element is going to kick one of the compounds or one of the elements out of the compound. Since zinc is a metal, it's going to kick out this copper. Okay? So that means that copper will end up by itself and zinc will end up bonded to the sulfate. Zinc is always a 2+ and sulfate is SO4 2-. These charges are equal and opposite, so we just get ZnSO4. This is actually already balanced, so we don't need to do anything for that. But I do need to write that it's single displacement. All right, for our last example, we have cesium reacting with bromine. Do you see that these are two elements? Anytime you have two elements, the only type of reaction that can happen is a combination reaction. So let's react these together. We'll have cesium and bromine make cesium bromide, so we just need to figure out what that is. Cesium is Cs+, and bromine is Br-. So when they react together, we get CsBr. To balance this, we'll put a 2, because we have 2 bromines on the left and we need 2 on the right, and then we'll put a 2 in front of cesium. And again, this was a combination reaction. You'll notice that none of these were decomposition reactions because I'm not going to ask you to predict the products of decomposition reactions. I'm just going to ask you to identify them. Alrighty, let's go ahead and pause here and work on problems number 7 on the Chapter 10 lecture worksheet. And actually, that is where we are going to wrap up today's lecture. We covered a lot of ground today. We learned about the 5 different types of reactions: combination, decomposition, single displacement, double displacement, and decomposition reactions. We learned how to predict the products of those reactions and then balance them. We also learned that there are some solubility rules that we need to follow and a few of them that we need to memorize. Remember, anything that's an alkali metal is always going to be aqueous, and also anything that contains the polyatomic ions ammonium, nitrate, and acetate. So those are the solubility rules that I want you to memorize, but everything else I will always give you that solubility table, and you can just find the intersection of the ions to determine whether something is soluble or not. Do make sure to get a lot of practice on writing these chemical reactions and especially predicting the products of double displacement reactions. We are going to use that skill in the next lecture when we learn how to write net ionic equations. So make sure you really are working hard to learn this material. And as always, if you have any questions, please send them my way. I am more than happy to help you, and I really do like talking about this stuff. So you're not bothering me, I promise. You can always ask me questions. But otherwise, keep working hard, and I will talk to you guys next time.